Good day. Again, this is the video for the solution of this problem for using the method of sections. So we are required to draw the shear and bending moment diagram of the given beam using the method of sections. After we have drawn the shear and bending moment diagram, we have to indicate the degree of the curve in each section and identify the absolute maximum value of shear and bending moment and indicate their locations with respect to point A. I will be labeling the diagram in the next slide. Okay, now this is our beam and we will draw the full body diagram of our beam. So, at first, I labeled the points A, B, C, D, and E. These are our change of load points. So, to label the support reactions, we have a fixed support at E. So, we would put a force along X, a force along Y, and we will assume a direction of movement counterclockwise ME. Before we solve these forces in class, take note that we first move this 250 Newton, this 250 Newton force to point C, here in point C. Because that is how we will determine the full effect of the 250 Newton force in our beam and not just in the hanger. So, to move the 250 Newton force at point C, what we did was to place it on directly at point C, the 250 Newton force, but we cannot just directly place it on point C because the principle of transmissibility will not be at work here since point C is not along the line of action of the force. So what we will do is we have to insert a moment here, MC. And MC is actually the moment of the 250 Newton force based on its original position at 2 point C. So that would be 250 sine 45 times 1. That is the moment of the Y component of the 250 Newton force acting. Take note that the force is acting at its original position first, and we're getting its moment about point C. And then negative 250 cosine 45 times 0.5, that would be the moment of its X component about point C. So the net moment is 88.38835 Newton meters. This is counterclockwise. So EX, we already have solved this in class. It's 250 cosine 45 Newton to the left. And then EY is 1926.776695 Newtons upwards. And we have solved ME to be 114.21356 Newton meter clockwise. Take note again that I told you in class, you can check these values if these are correct. How? By summing moment at either point A, B, C, or D. Don't sum moment at point E because that is where your supports are and you would not be able to check the value of EY. So the moment should be 0 for equilibrium. Now, after solving for the supports, we will move to sectioning the beam to determine the equations that will give us the shear and the bending moment at each section of the beam. So how many sections of the beam will we have in this particular beam? So from A to B, that is one section. We section at a point somewhere between A and B. And then B to C. So C is your next change of load point. So another section there. And then from C to D, another section. And then lastly from D to E. So we have 4 sections here. Okay, So we would now do section AB. Take note that I have already discussed this to you in class. We will just recap. So section AB would be somewhere between A and B here. Since the left side of the section would be shorter, a lot shorter than the right side, we would of course use the left side of the section. The applicability would be from 0 to 1.5, x being 0 to 1.5. Take note that the leftmost end of the beam would be x is equal to 0, and the rightmost end of the beam would be x is equal to 13, or the total length of the beam. So the equations that we would be getting in this section would be applicable from x is equal to 0 up to 1.499999, or almost 1.5. Drawing the section, we have the trapezoidal load, but take note, of course, the leftmost end of the beam, the height is 100 Newton per meter. However, at the right side of the section here, in this point, this cannot be 300 Newton per meter because we sectioned the beam in between A and B. So, the length of the section is an arbitrary length, x. The length is arbitrary so that we can have an equation that will be applicable for the whole section. If the length it has a particular value or magnitude, say 1, it would only be applicable at x is equal to 1. So since we use the left side of the section, we would put a downwards shear force and a counterclockwise moment. We will label that as VAB and MAB. So take note that this should always be your assumption if you're using the left side of the section. Now, as I've said earlier, the height of your trapezoid in your section is not 300 Newton per meter because we sectioned in between A and B. So the height, as we have solved in class, is 200 all over 1.5x. Again, to recall, where did this come from? So we used similar triangles. Our triangle would have a base of 1.5, so that's the base of our trapezoid. And then the height of our triangle is the height in one side of our trapezoid, which is 300, minus the height of the other side, which is 100. So 300 minus 100 is 200. And the similar triangle, the one in our section, has a base of x and a height of h. By similar triangles, h over x is equal to 200 all over 1.5, and that gives us h to be 200 all over 1.5 times x. There. Also, take note that the 300 Newton force here, this one, that is directly acting at point B, should not be in your section. Why? Because you section the beam in the middle of A and B. Okay? So if you place the 300 Newton force there in your section, you would only get the shear force expression at x is equal to B, or at x is equal to 1.5 at point B. So you would not be able to solve for the shear at, say, x is equal to 0.5, x is equal to 1. The equation would not be applicable there. Okay? So here is our summation of forces along y. I use the old convention of upwards positive, downwards negative. So that the rectangular force, negative 100 times x. X is the base, 100 is the height. And for the triangle, it's 1/2 base times height. So here's the 1/2. And then x is the base, and 200 all over 1.5x is the height. Then, of course, you would subtract your VAB as well. So, simplifying the equation, we would have VAB is equal to negative 100 times x minus 100 all over 1.5x squared. Next, we would be summing moment. So, summation ng moment, again, please be reminded that we are summing moment here at the section. so that VAB would not have a moment at anywhere at that point. Okay? So, of course, we have the rectangular load. It's base times height, 100x, and then this is the moment arm, x over 2. For the triangular load, again, it's 1/2 base times height. That's the area, and that's the total force. And the red text here, x over 3, is the distance of the centroid from the section. So it's all counterclockwise from the section. And MAB is assumed to be counterclockwise. So plus, and so we simplify the equation we got. MAB is equal to negative 50x squared minus 100 times 4.5x cubed. Okay. So next, we would be considering the section from B to C. Again, we will section at the middle of point B and C. Not at the exact middle, somewhere in between B and C. We would still be using the left side of the section since it's still quite shorter than the right side of the section. So again, the applicability of this equation is from 1.5 to 5.5. Again, x is equal to 0 being the leftmost end, and x is equal to 13 being the rightmost end. So if that would be our applicability, 1.5 to 5.5, then we have to label the whole length of the section as x. Okay? And of course, our trapezoid now is full. Again, it's not sectioned. So the height of the trapezoid is 300 Newton per meter. The base is 1.5. Therefore, this length over here is x minus 1.5. And then don't forget, we can now include the 300 Newton force in this diagram. Also, don't forget your downward force, VBC, and your MBC. Okay? Take note that if you use X in this portion only, if you represent this portion, this length here, as X, if you would use that representation, then your applicability would not be 1.5 to 5.5. Your applicability would be 1 to 4. So, no, 0 to 4 rather. This length, the length from B to C. That's what you would be substituting in your equation. 0 to 4. And your x is equal to 0 would now not be the leftmost end of the beam. Your x is equal to 0 would pertain to point B. So that's why I'm not keen on using this, because you might get confused what value of x you would be substituting in the equation. So we would not be using this representation. Okay. Now, again, we sum forces along y. So this one here, this term here is for the rectangle, 100 times 1.5 here in your trapezoid, this part. And then this one, 1/2, base is 1.5, height is 200, 300 minus 100. And then this negative 300 here is for the concentrated load. And then our uniformly distributed load, you don't have to use similar triangles there because it's constant. It's just 400 times x minus 1.5, the area of the rectangle. And then don't forget your VBC. So simplifying the equation, you have VBC is equal to negative 600 plus 400 times x minus 1.5. Then we sum moment. So again, for the rectangle, here the area is 100 times 1.5, so that's the force. And then here is the distance of the centroid of the rectangle from the section. Again, we're summing moment at the section. So the whole length of the section is x. The base of the rectangle is 1.5, so 1.5 over 2, x minus 1.5 over 2. Now for the triangle, here is the area of the triangle, 1/2 base times height, and then this is the moment arm. X minus, this whole thing x minus 2/3 of 1.5, because 1/3 of 1.5 is measured from point B here, there. So that's 2/3 of 1.5 measured from the leftmost end of the B. And then for the concentrated load, it's simply 300 times x minus 1.5. Take note that they are all positive because it's counterclockwise from the moment, about the moment. The moment is counterclockwise about the section. And then, lastly, negative 400 times x minus 1.5, that's the area of the rectangle, and x minus 1.5 over 2 is the distance of the centroid of this large rectangle here from the section. Don't forget plus MBC. And simplifying the equation, we have negative 150 times x minus 0.75 minus 150 times x minus 1 minus 300 times x minus 1.5 plus 200 times x minus 1.5 squared.